Hello everyone, my name is Alexandre BROCHARD. In today's video, I'm going to present our results for the Phased Array Signal Processing Student Challenge at EUSIPCO 2025. So for the outline of this presentation, first I'm going to introduce the context of the challenge. Then we'll enter into the details of the two proposed solutions. And finally, there will be a short conclusion about the results that we've obtained. So, for the context, basically we have a data set and it is composed of IQ samples. Those IQ samples are collected through an antenna array, which is composed of 4 different antennas. As you can see, there is a picture of the four different antennas on the bottom of the slide. And in this context, the antenna array should receive the GNSS signals to compute the position. And we also are going to have jamming signals coming from a jammer. And we have some information about the jammer. We know that it will send a noise signals, which could be which should be a PRN, so pseudo-random noise. And the power of the jammer will increase over the time. So at some point in time, the jammer will be so powerful that the GNSS receiver should not be able to compute its position. So, what we want to do, basically with the challenge, we need to cover up 3 objectives. So we need to detect when the jammer's action starts. We want to localize the jammer, of course, and we also want to mitigate the effect of the jammer. We need to cover all the 3 objectives during the time of the jammer's actions. And in order to fulfill those objectives, we are going to use some array processing techniques. So for example, we are going to use beamforming because by using beamforming, we are going to retrieve some signals of interest. So in some case, the GNSS signals, or maybe in other cases, we want to retrieve the jammer, the jamming signal. And by focusing on one direction, we are also going to mitigate in the other direction, on the other directions. So we should be able to mitigate the jammer. And we're also going to need some direction of arrival estimation in order to localize the jammer. So this is our formulation of the problem. So basically, we put our referential frame at the center of the antenna array, and at each upcoming signals, so the GNSS signals and also the jamming signal, because of this consideration of the referential frame, basically there will be a phase shift between the 4 antennas. And so this phase shift will induce some steering vectors that will have an influence of the received signal. And we are going to use this information in order to compute the direction of arrival of the different signals. So now for the 2 proposed solutions, basically we have proposed an offline solution in order to detect and to localize the jammer and to focus on those 2 parts. And then we have proposed a real-time solution, which is the online solution, where we also try to mitigate the jammer. So for the overview of the 2 solutions, basically the dataset is composed of the 4 different antennas with row observations. So we have 4 different files, one for each antennas. We are going to process the dataset with MATLAB, and then in output we are going to have some filtered observations. We are going to use those filtered observations and going to feed the GNSS SDR with those filtered observations to try to compute the true position of the GNSS receiver. So in this presentation, basically when I'm going to present the offline and the online part, I'm going to focus mainly on the MATLAB part. So we're going to start with the offline proposition. So the main idea here is very simple. Basically, we know with the context of the challenge that the jammer and his power will increase over the time. So we're going to focus and to select only the last samples which correspond to the last seconds of the jammer's action. we should be able to detect and to also estimate the direction of arrival of the jammer. And by doing so, we are going to create a beamformer by selecting the corresponding string vectors, and so we are going to compute the right weight vectors in order to focus in the direction of the jammer. What we want to do here is, because when we are focusing on the direction of the jammer, we should be able to detect it as soon as possible, because we cannot focus more on his direction. And so the main idea here is to retrieve the direction of the jammer, then focus on this direction and try to detect the jammer as soon as possible. So those weight vectors are going to create our beamformer. Then we are going to use as input the raw data, and then we are going to have some filtered observation, and then we will try to detect the jammer. So we have two plots on this slide. Basically, on the left, we have the raw observations, the power of the raw observations, and on the right, we have the power of the filtered observations. So for the beamforming techniques, we use a minimum power distortionless response, the MPDR, which is a classical beamforming techniques in the literature. So what we see on the left, so with the raw observations, we can observe that there is a slight increase around 130 seconds, so around 2 minutes and 10 seconds. And we assume that this slight increase, this slight change in power, should be the consequence of the jammer's action. And so we are going to try to also find that same behavior in the filtered observations. So we found also the same behavior, but sooner than in the raw observations. With the filtered observations, we observe that we have also this slight increase in power, but around 106 seconds, which correspond to 1 minute and 46 seconds. So in the end, with the offline proposition, we have been able to localize the position of the jammer, and we have been able to detect it, and we know when the jammer action starts, because we can focus more on the jammer that using a beamforming techniques in his direction. So now we are going to talk about the online proposition. So now, because we know with the offline proposition, we have been able to detect the jammer, and we have been able also to localize the jammer. Now we are going to mitigate it. So the idea here, the main idea here, is to focus on the direction of the GNSS signals. So at the zenith, just above the GNSS receiver. So by focusing on this direction, we will compute some weight vectors to create a new beamformer. Then with this new beamformer, we'll have some new filtered observations. With those filtered observations, we are going to also try to detect the jammer, of course, same as the offline proposition. But now, because we now should have mitigated the jammer, we are going to feed GNSS SDR with the filtered observations to see if we are going to found the true position of the GNSS receiver. So, for the detection and localization part, we have used music, which is an algorithm to estimate the direction of arrival. Technically, we find the same azimuth angle, but again, we are not able to detect it as sooner as we should be, because we detect it only at 2 minutes and 10 seconds. But we are still able to detect the jammer and to localize it, even if we focus the beamformer in the zenith direction. So now we are going to focus on the filtered observations. So we have given those filtered observations to GNSS SDR, and now we are plotting the Earth-centered, Earth-fixed position, so ECF positions, and we have been using, sorry, the GPS L1 signals. So on this graph, we need only to focus on the green color, which is our filtered observations. The other color are corresponded to the 4 different antennas, so they are the raw observations. As you can see on this graph, we can see that there is like much variations, because the jammer's action and also the jammer power is increasing, as I recall you. But there is an interesting point. At some point in time, the jammer's action, the jammer is so powerful that the GNSS receiver is not able to compute the true position. But with our mitigation technique, which is really simple, we are still able to compute the true position of the GNSS receiver. So it ensures us that our mitigation techniques works quite well and we don't need a complicated technique in order to mitigate the jammer. So in order to have a more visual result, we have plotted also the true position of the GNSS receiver on the Google Earth using a .kml file, sorry. And so as we can see, the position is not variating that much. So we are quite sure that we found the true position of the GNSS receiver. And because if we are plotting the position of the row observation, we should have more variations, and at some point we should not be able to find the true position. So, to conclude, basically we have proposed two array processing approaches. So one offline, when we study all the data set and we select the final samples in order to create a beamformer. What happened is that we have been able to cover the detection and the localization part. And we also implement an online, so real-time solution. And we cover up also the detection part and the localization part. And we also cover the mitigation part. And we've been able to compute and to find the true position of the GNSS receiver. So finally, I'm going to talk about some numerical results. So for the offline part, we have like 146 seconds. So, sorry, 1 minute and 46 seconds. And with the online part, we have 2 minutes and 10 seconds. So we detect it later, even if we cover up the mitigation, and even if we mitigate well the jammer's action. Also, for the duration of arrival of the jammer, we find some results that are not very current to us, because for the elevation angle, we found that we have obtained 30.1 degrees. And even if you see at the topography of the area, of the region, we can see that 30.1 degrees seems a bit high, even if we have mountains, and we think that the jammer is at the top of one of the mountains in the area. We found that 30.1 should be too high, but at the end, it's not really relevant because we are able to estimate the rad subspace of the jammer. And at the end, we use this subspace and we don't focus on it. So we mitigate anyway the jammer's action. So it's not really relevant because we are still able to localize it, even the azimuth is well, but the elevation angle, we are not really sure about it. And we've been able to mitigate the jammer with the online approach. So thank you all for listening to this quite short presentation. If you have some questions, feel free to ask in the comments. And thank you all, and thank you again, EUSIPCO, for this really interesting opportunity and to work with this GNSS Jam dataset. Thank you all, and see you soon at maybe a next conference at EUSIPCO 2026. Bye!